Okay, now page 2 of Applications of Differential Calculus. And I don't know how you felt about that visit to memory lane, derivatives found by first principles, a lot of algebra. Luckily, I think we're through that. We will go back to just taking regular derivatives. So here we are on number 4. And let's see. It says an object moves in a straight line with displacement function s of t and velocity function v of t, where t is greater than or equal to 0. State the meaning of these two limits. And so basically what this is saying is that this is like the first displacement minus the second displacement divided by the two times for each displacement. Okay, and so basically it's saying that the second displacement is at time 4 plus h, and the first displacement is at time 4, but they're making those basically equal. So it becomes the tangent line, like let's say that this is the function s of t, and this is t equals 4. So basically what this is saying is, hey, the average velocity, except for they push the t1 and t2 together so that it's basically a width 0 triangle. And remember, this is like basically saying the tangent line at this point, the gradient of the tangent line is this. So the gradient of this tangent line basically means the derivative. So the derivative of s would be the change in s over the change in t, which is the instantaneous velocity. Okay? So it's the instantaneous velocity at time equals 4 seconds. And this one here, you see that's the v4 plus h minus v4. So this would be the derivative of velocity, which would be acceleration. So this would be the instantaneous acceleration at time equals 4 seconds. So it might take you a little bit of time to wrap your head around that, but just to remember, like we said before, that acceleration is the derivative of velocity, and velocity is the derivative of displacement. Okay. Let's see. Put the appropriate number of derivative dashes to make true. Okay, so displacement is s of t. Velocity is v of t, but this is incorrect, right? Velocity is not equal to displacement. But if we put a dash there, we have that the derivative of displacement is equal to velocity, and that's true. Acceleration. We know that acceleration is a, but a is not equal to v. Oh, that's right. If we put a dash, then the derivative of velocity is acceleration. And remember that velocity is equal to the derivative of displacement. So if we take the derivative of velocity, it's like taking two derivatives of displacement. Okay, so now those statements are true. Okay, so now let's interpret the following. The displacement is 0. So that just means that you're at position 0. Okay? At the origin is another way to say it. What about s of t is greater than 0? That means you're to the right of the origin. What about when s of t is less than 0? That means you're to the left of the origin. What about velocity? When velocity is equal, what does that mean? It means you are at rest. What about when the velocity is greater than 0? It means you are moving to the right. And what about when v of t is less than 0? That means you're moving to the left. What about acceleration? What about when acceleration is 0? That means you are at constant velocity. What about when acceleration is positive? It means you are accelerating to the right. And what about when a is less than 0, that means you're accelerating to the left. Okay? And so that gets into some weird situations like you figured out in the investigation. Like if you have velocity moving to the left, but you have acceleration moving to the right, you have them going in different directions, so that actually means you're slowing down, right? So if your acceleration is going one way and your velocity is going the other way, then you are slowing down, right? Because the acceleration is trying to make the velocity change in the other direction. Okay. And here's a table which tells us different phrases that you're going to encounter when you look at these word problems, such as initial conditions. That basically means the time equals 0. At the origin, that means s is at 0. Stationary, that means the velocity is 0 or it's at rest. The direction reverses, that also means that the velocity is 0, because like the direction reverses means that it was going in the right direction and then all of a sudden it starts going in the left direction. But to go from the right and change to the left, it does need to stop momentarily and the velocity becomes 0. Maximum or minimum displacement. So that would be when it gets to a very large value of s, but then it starts to decrease. So the velocity, again, would be momentarily 0, or it's like at the smallest possible value of s, but then it starts increasing, and the same thing's going to happen. The velocity is going to be momentarily 0. Constant velocity, acceleration is equal to 0. And maximum or minimum velocity, also there is going to be a moment where the acceleration is equal to 0. Okay? All right. Speed is a scalar. The the magnitude of the object's velocity. Okay? Okay. Now we do the problem here. An object moves in a straight line with the position given by this function, which says the displacement from the origin, where t is in seconds, it's a positive number. Find the expression for the object's velocity and acceleration. Draw a sign diagram for each function. Okay, now this is a lot easier when we just take derivatives. Remember that velocity is the derivative of displacement, and acceleration is the second derivative of the displacement. So let's just do that. We're going to take the derivative of displacement, and we'll get 2t minus 4, and that will be the velocity function. And then we're going to take the second derivative of that, and then we'll get 2. Right? We just take the derivative of that, and we get 2. So now we have answered A. Okay? Expressions for the velocity and acceleration. Now let's try to draw a sign diagram for each one. So let's first draw a sign diagram for velocity. And it looks like the 0 point is going to be when t equals 2, right? When t equals 2, then velocity is 0. What about when t is bigger than 2? I'm sorry, I just wrote t. It's supposed to be 2. Okay, so this is our t, and then so the velocity value is going at 2 is going to be 0, and at greater than 2, it's going to be a positive number, and when it's less than 2, like negative a billion, then it's going to be a negative number. Okay, so that's our sign diagram for velocity. Let's draw a sign diagram for acceleration now. Let's see. Actually, the acceleration is always 2, no matter what the time is. So it's positive 2, so it's always positive, right? That was kind of a simple sign diagram. Okay. That was A. Okay. What about B? Find the initial conditions and explain what is happening to the object at that instant. So the initial conditions would be putting t equals 0 in for each function. So like, for example, s of 0 is equal to 0 minus 0 plus 3. So it would be 3. And v of 0 would be 0 minus 4, so negative 4. And a of 0 would be equal to 2, as always, right? Okay, so what is happening to the object at that instant? Okay, so the object is at position +3, moving left at 4 meters per second, and I think like slowing down at a equals 2 meters per second squared to the right. Okay, so that's kind of describing what's happening there. So, like, do you see how the position is 3, positive 3. The velocity is moving to the left at 4, and it is the acceleration is going to the right at 2. So it's actually slowing down because the velocity and acceleration are in opposite directions. Okay, so that was B. Now let's look at C. Describe the motion of the object at time t equals 2. Let's see, at t equals 2, then S is equal to, let's see, 2 squared minus 4 times 2, so it's 4 minus 8, negative 4, plus 3 is negative 1. So the position is negative 1. The velocity is equal to, let's see, 2 times 2, 4, it would be 0, and the acceleration, of course, is 2. So, basically, the object is stopped at this instant, but it is about to move right because the acceleration is +2, and so even though it's momentarily stopped, it's about to move right. So that was the answer to C. Okay, and then this one here is the answer to B. What about D? At what time does the object reverse direction? Find the position of the object at these instants. Okay, so basically the object reverses direction. And remember, we looked at this thing. When it's reversing direction, it has the velocity equal to 0. So if we just look at our sign diagram, we can say that the velocity is 0 at t equals 2. So, and I think that's the only place that it's t equals 2. So for D, we're going to say, at what times does the object reverse direction? At t equals 2. Find the position of the object at this instant. So it's at s equals -1. We just found that. Okay? It will reverse directions from going left to going right. Okay. What about E? Well, draw a motion diagram for the object. Okay. So a motion diagram is basically it's like a number line with arrows or something. So let's draw one here. So basically, at s equals 0, we know that the position is 3, right? If you put 0 in for the t's, you're going to get 3 out. So we start, ooh, yuck. That's better. Okay, so we're going to start at s equals 3, and that's our starting point. And then, which way are we going at that point? Well, at t, this is t equals 0. So at t equals 0, it's at position +3, and the velocity is negative. So it's going this direction, right? And then, and at some point, it is going to turn around, which we just found here. At t equals 2, and at s equals -1, it's going to go from left, and it's going to start going right. So it's like that instant right there. So this is going to be at s equals -1, it's going to turn around.
And then basically it's going to continue like that forever because the velocity is going to be positive forever after, right? Because like, look at this. So the velocity is negative, so it's going to the left, and then when it gets to t equals 2, it's going to start going to the right. So I'm going to mark this point here, t equals 2. And you can see at t equals 2 that s equals negative 1, and that's why this is negative 1 here. And then it turns around and it's moving to the right instead. So that's a motion diagram for the object right there. Now we'll look at f. So f says, for what time intervals is the speed of the object decreasing? So that would normally you would say, okay, it's decreasing when the acceleration is negative, right? When the acceleration is negative, normally the speed is decreasing. But this time, remember that when the acceleration is in the opposite direction of the velocity, it's decreasing. Not necessarily that when the acceleration is negative, it's going to be, the velocity is going to be decreasing. I mean, here we're talking about speed. And the reason why they say speed is because if you say the velocity is decreasing, then you might think, oh, the velocity is getting more negative. But like, if you're going to the left and the velocity is getting more negative, the thing is actually speeding up, right? So basically we're saying, when is it going to start moving slower? And that's basically when the acceleration is in a different direction than the velocity. And that would be like in this region here or this region here, right? Here the velocity is negative. Here the acceleration is positive. So you're moving in opposite directions. So that means that the thing is slowing down. So basically that is between between 0 and 2 seconds, right? That's the answer for F. So between t equals 0 and 2, that's when the acceleration and the velocity are in opposite direction. So the speed of the object is decreasing.
And that's it for this problem.